yesterday we looked at the auxiliary point method, and also we did an example with that, and then looked at how the analytical method using the loop closure equation essentially gives you. So, what we have been doing with the graphical method is not anything different, it actually derives from the loop closure equation that you write for the mechanism, and when you differentiate that for the velocity. So, for a mechanism where we could not use the, or for a kinematically complex mechanism, let us just look at applying the analytical method. So, a mechanism with more than one loop, ternary or higher order floating link, let us just look at doing it analytically. Okay. So, velocity analysis. So, this the methods that we looked at were, if this is the input, we found we can't directly solve using the velocity difference method. So, you either use inversion in this case, because inversion actually makes this a simple mechanism. Yesterday of course, we saw a mechanism where that would also not help, but so in this case inversion would help to solve for the velocity analysis. Of course, the auxiliary point method is also gives you a direct way of solving it without using inversion. So, now we look at the loop closure equation to solve this analytically. Okay. 2, 3, 4, 5, 6. Again, ensure that this, always check for mobility when you see when you encounter a new mechanism. This of course, we have seen this a few times now, but this is a mechanism of mobility 1. It is basically a 6 bar Stephenson mechanism. So, I have this. I will call this 3 dash, let us say this angle is gamma. So, I have 2 loops in this problem. So, call this 1 dash. Okay. So, one loop is 1, 2, 3, 4, the other loop is 1 dash, 4, 3 dash, 5 and 6. I can even take 5 this way. No particular reason, but you can do that. Okay. So, if I write the 2 loop closure equations, I have, let me write the 2, R2 plus R3, these are all vectors, equals R1 plus R4. Okay. This is the first loop, and the second loop is R4 plus R3 dash equals plus R6 plus R5. That is my second loop. Okay. So, assume the position analysis is done. Like I said, analytically position analysis is difficult, but what you can do is, so for a specific position, even finding the position of all the points in the linkage may be a challenge. Okay, because for this one, for instance, if I give you this angle as the input, okay, knowing all the link lengths, getting this point is still going to be a challenge. Okay. So, typically what you would do is, you would say use some other link as input and have a range of positions, you simulate it for a range of positions that you are interested in. Okay. So, for instance, if I give 2 as the input and I have the position data for the range that I am interested in, then I can just pick whatever position I want then to do the velocity analysis. Okay. I can write these as R2 e power I theta 2 R4 e power I theta 4. Then when I differentiate this with respect to time, I get I R2 omega 2 e power I theta 2 plus I R3 omega 3 e power I theta 3 equals R1 does not change. I get I R4 omega 4 e power I theta 4. Okay, so this is one velocity equation. For the second one, I have R4 second loop, I have R4 e power I theta 4 plus R3 dash e power I. What is the angle for 3 dash? I have, yeah. So, I can express it in terms of the angle for, so this is angle of R3, R3 plus 180 minus gamma, because this is all part of the same rigid body. So, gamma is essentially a constant. Gamma plus, or I could take gamma as this angle, in which case it would just be theta 3 plus gamma. Instead of choosing gamma like this, I can, it's just a constant angle between 3 and 3 dash because they belong to the same rigid body. That is not going to change with time. This is equal to R1 dash e power I theta 1 dash plus R6 e power I theta 6 plus R5 e power I theta 5. Okay, this is when I differentiate this, I don't want to call this 2. This is the position, first equation for the position, second equation for the position. This is the first equation for the velocity. When I differentiate this, I get I omega 4 R4 e power I theta 4 plus I R3 dash will still be omega 3, right, omega 3 R3 dash e power I theta 3 plus pi minus gamma is equal to R1 dash does not change with time, I omega 6 R6 theta 6 plus I omega 5 R5 e power I theta 5. This would be my second velocity equation. Okay. So, these are both vector equations, V1, all of them are vector equations. So, I am looking at velocity. So, all my position analysis is completed. Position analysis is complete. Implies all thetas are known. Okay. Input, velocity input is omega 6 here. Okay. So, I can now if I look at V1 and V2, I can get two scalar equations from V1, two scalar equations from V2. and my unknowns, what are my unknowns? Omega 4 and omega 5. Okay. So, I have 4 equations, 4 unknowns. I can just set it up. These are my unknowns, this would be the known quantities. So, if I take V1, this is unknown, right. So, I have I R2 multiplied by omega 2, I have I R3 multiplied by omega 3 minus I R4 and a 0, okay, from V1. V1 gives me this. From V2 I have and this side is 0. So, I should actually have 4, right, 0 0. Then from this one, from V2 I have I R4, okay, omega 4 this position, this is I R3 dash, okay, and omega 5 minus I R5. When I bring this to this side, there is no omega 2 term, and on this side I will have I omega 6 R6 cos theta 6, I omega 6 R6 I square omega 6 sin theta 6. Okay, just when I expand each of these, gives you 2, right. So, I would equate. So, each of these, this is 2 equations. Instead of splitting them up and writing in terms of cos and sin, I have just put it in vector form. Okay, but this is 2 equations, this is 2 equations, 4 scalar unknowns. I can solve this for omega 2, omega 3, omega 4 and omega 5, simultaneously solve for these 2. Okay. So, analytical methods are always applicable. You can do a simultaneous solution for, it does not really matter whether it is a complex or mechanism, as long as you, because the velocity equations are linear. Position is a different story. That is why you typically just simulate for a range of positions and then, okay. So, this is how you do the velocity analysis for multi-loop or complex mechanisms. Set up the equations and solve them. The thing is, if you want, if you are interested in one particular position, or the graphical is a lot easier to do, and a lot more, you can get a feel for, okay, how is this mechanism going to move. Okay, if I give it this input, how is my output going to be? You get a much better feel for it than with all these equations. So, this is I will let you try the problem that we did yesterday with the 2 inputs. Same thing, you can set it up. The difference is one of the link lengths will be changing. One of the vectors, the length will also be changing, as opposed to here where it is all rigid links in the mechanism. Okay. We will move on to acceleration analysis now. The ultimate objective when you are doing an analysis is to basically, like I said, you know what you are going to do with your project is determine the actuation torque or force required for the problem. Okay. And in this case, what you may be able to do a quasi static analysis. So, you may be able to get away with not knowing the accelerations. Okay. You only need the weights of the members, but you may be but if you are operating things at high speeds, the inertial accelerations could be much higher than gravity or other accelerations, in which case you cannot neglect that. Those will be the major sources for force in the mechanism. So, the ultimate aim would be to calculate those inertial forces, in which case you have to do the acceleration analysis for the mechanism, and that can be done only after you do the position, velocity, and then you do the acceleration analysis, because the ultimate objective is your inertia force analysis. You need to determine the forces, because you need to be able to see whether the links that you have designed can withstand the stresses that you subject them to. Yes, Jayant. So, one of the important things when you are doing acceleration analysis is to ensure that all the acceleration components are expressed in the same coordinate system, which is an inertial coordinate system, which is a coordinate system fixed to the usually the fixed link of the mechanism. So, all, because Newton's law applies only in an inertial frame of reference. Of the fixed link. And the path of the point of interest should be known in this frame in order to be able to find the acceleration. So, we will look at, you know, similar to the velocity analysis, we will look at accelerations of points that are on the same rigid body. We will see what is the acceleration difference between 2 points that are on the same rigid body. We will also look at cases where the 2 points may be on different links. They may be and how we would then express the acceleration of those points depending on the relative motion between the links. Okay. So, let us first look at the simplest case of a single of a link rotating about a fixed pivot. Okay. So, note position and velocity analysis must be completed before that is, at least for the position of interest. Okay, because there will be quantities from the position and velocity analysis you will need for the acceleration. They need to be known before you can solve for the unknowns in the accelerations. Okay, so let us take the case of a point A on this rigid body, okay, that is defined by this vector I theta I. So, we saw that the velocity of A would be omega 2 I omega 2 r A e power I theta A, because the velocity is dRA by dt. All the capitals are vectors. The acceleration of A is defined as the rate of change of the velocity. So, if I differentiate this, okay, in this case RA is a constant, right, because O2A is part of this rigid body, RA is a constant. I get I d omega 2 by dt RA e power I theta A, plus I also have this term here. So, I omega 2 RA d of e power I theta A by dt. So, this gives me I alpha 2, the change in the magnitude of omega 2 is called the angular acceleration alpha 2 R A e power I theta A, plus this is I omega 2 R A, this is again omega 2 I omega 2 e power I theta I. Okay, this. So, this gives me I alpha 2, I can write this as the vector R A minus, because I into I, minus 1 omega 2 square R A this. Okay. This is your familiar tangential acceleration, tangential component of the acceleration of A, and this is your normal component of the acceleration of A. So, again tangential component is a scaled version of R A rotated 90 degrees in the direction of alpha 2. So, for planar mechanisms you can take alpha 2 as plus or minus depending on whether it is counterclockwise or clockwise, and you have. So, the direction is rotated pi by 2 is so magnitude is alpha times R A and direction is obtained by rotating R A 90 degrees in the direction of alpha 2. Similar to what we got for the velocity. There in the case of velocity you had the position vector rotated 90 degrees in the direction of omega 2, here it is in terms of alpha 2. And this is your radial or normal component. And it is along R A, but directed towards the center of rotation. So, it is opposite to the direction of R A. This you would have seen several times when in earlier classes. So, this is the expression for, so I can write this as minus omega 2 square plus I alpha 2 R A. So, the tangential acceleration, the I alpha 2 alpha 2 r component is because of the change in the magnitude of omega 2. Okay. So, if it is rotating, if something is rotating at a constant angular velocity, you do not have alpha 2, alpha is going to be 0 because the magnitude of omega is not changing. This arises because of the change in the direction of the velocity vector, change in the direction of the velocity vector. So, that is why even if something is rotating at a constant speed, constant angular speed, you still have an acceleration because the direction of the velocity vector keeps changing. Okay. And that component is the radial or the normal component, centripetal component also. This is due to the change in the direction of the linear velocity of that point. The other equivalent form for the normal component is V A square, the magnitude of that would be V A square by R A. Okay, this is also equal to minus omega 2 square R A. So, the special case when point A moves in a straight line, what is R A? R A is infinite, which implies the normal acceleration is 0 from here. Okay. There is no rotation, right, but from here you can have a particle, you can have a body, a point moving along a straight line with a particular velocity, and its normal acceleration will be 0. So, its only component is the tangential component, which makes sense, right, which whatever direction the particle is particle or the body is moving is linear motion is an example of this, where the radius of curvature is infinite. So, similarly, if I have another point B on this link, okay, then its absolute acceleration a b equals minus omega 2 square plus I alpha 2 into r b e power I theta b. Okay. So, the direction of its tangential, even though it is the same, this factor is the same, r b is changing as well as, so there is an acceleration difference between the 2 points, even if the link is rotating at a constant angular velocity. Okay. So, even if alpha 2 is 0, omega 2, so alpha 2 and omega 2 are for the link, but specific points will have different accelerations because that will depend on where they are located on the link. So, there is an acceleration difference between B and A, and what that means is, suppose I am sitting at point A, what the acceleration difference means is, and there is a coordinate system that is located at A, but does not change its orientation with respect to the global coordinate system. So, if this is the global coordinate system attached to the fixed link, if I have a coordinate system that is pinned at A which does not change its orientation with respect to the inertial coordinate system, and I observe the acceleration of B from that coordinate system. Okay, so, I am sitting at A. Okay. I am a particle sitting at A and I am observing the acceleration of B from a coordinate system that remains parallel. Even as the link is moving, this does not change its orientation with respect to the ground coordinate system. If I observe the acceleration of B, that is the difference, acceleration difference that I am talking about. So, what is that acceleration of B? So, the acceleration of B with respect to A is the acceleration of B with respect to my fixed orientation coordinate system attached to A. So, fixed orientation with respect to the ground coordinate system. It remains parallel to the ground coordinate system. It does not change its orientation with respect to time. Okay. Typically, you take them as parallel. Okay, so this would be, so I can write this as acceleration of B to A. So, each term has two possible components. So, this would have a tangential component and a normal component. This would again have a tangent, we saw each of these accelerations has a tangential and a normal component. Similarly, there is really no difference, you know, it is like my sitting at O2 and observing A was, now I am sitting at A and observing B. So, this relative acceleration will also have a tangential component and a normal component. So, in the case of 2 points that are fixed on a rigid body, the thing is the tangential direction of this is not the same as the tangential direction of something else. Okay, so, you can't just club, I can't say I will equate all the tangential components. Okay. So, they have different directions. Okay, tangential component of B is along a different direction. So, it is relative when we talk about tangential and normal, it is with respect to the path of that particular point. Tangential to the path of B, normal to the path of B. Similarly, for A and for B relative to A. Okay. So, this, so N and T refer to the normal and tangential components with respect to the path of the okay. Because A and B are points on the same rigid body, The reason that this acceleration difference also has the same form is because if I sit at A, B can only move in a circular path with respect to A. B cannot move, we saw that with the velocity, right. The velocity component is necessarily perpendicular to AB, and from that you see that the acceleration will again have a tangential component and a normal component, because the motion of B relative to a reference frame that is fixed at A is the same as or similar to the motion of B about O2 or the motion of A about O2. So, you will have the same two tangential and normal components. Okay. So, let us look at, we will yes.
So, acceleration of B with respect to A normal is along the line joining AB.
Yes, towards A.
Towards A.
Towards A. It is always towards the center of rotation. And the tangential acceleration will be in the direction of alpha 2, 90 degrees. So, this vector AB, okay, this rotated 90 degrees in the direction of alpha 2 and scaled by alpha 2. Okay. So, if I have, if this is R of B relative to A, okay, and my alpha 2 is counterclockwise, then this would be tangential component of this thing. If R, and it will be scaled by, so this will be, magnitude will be alpha to R here, or I can just say AB. Here, if this is the vector and my alpha 2 is clockwise, then this would be my acceleration, tangential component alpha 2 into AB. Same magnitude, different direction depending on the direction of alpha 2.